Okay, so in this video I'm going to take a look at simple harmonic motion, but in the context of a pendulum. So this video is designed to follow up from the video I did on SHM for a spring system. So if you haven't watched that yet, I'd highly recommend you do that first. So let's get cracking. So just to refresh our memory, simple harmonic motion is when the acceleration is directly proportional to the displacement from the equilibrium position and always directed back towards the equilibrium position wherever it is, so in the opposite direction to the displacement. So let's first think what an equilibrium position is for a pendulum. So here is my very high-tech pendulum I've made from a tennis ball and a string. Works pretty well. So if I just hang this up and let it rest, just like I did with the springs, this will be the equilibrium position. So at this position, the tension force from the spring on the tennis ball is equal to the weight force of the tennis ball here. And that's why it's not moving if I can stop shaking, and so the resultant force is 0 there. So this is the equilibrium position, so we can see that when it's not displaced from the equilibrium position, or displacement is 0, there is no resultant force and no acceleration. So our first condition of SHM is working there. So what we're going to do is we're going to displace it from the equilibrium position, and we're going to look at how the resultant force changes with the displacement. And I'm going to look specifically at the horizontal displacement. So essentially making like a right angled triangle across here, like we can see in this diagram here. So something like that. Okay, so that's what we looked at the equilibrium position, so let's now displace it. So what we're going to do is we're going to look at resolving the forces. So when we have the tennis ball swinging, a useful thing to notice is that although it swings, it doesn't move relative to the string. So it doesn't like come up towards the point I'm hanging it from or further away. So if we resolve the weight force into two directions, like you can see here, we know that W cosine theta is equal to the tension force from the string, and theta being the angle to the equilibrium position there. So we know the resultant force is given by W sine theta. So that's the first one. Now, what we can do is we can make a substitution for sine theta. So if we click back here, we know that the opposite side of the angle is the horizontal displacement, and the hypotenuse is the length of the string. So if we put that in, that's what we've got here. Sine theta is the horizontal displacement divided by the length. So our resultant force is actually the weight force times x over L. So we can see that the resultant force here is directly proportional to the displacement. Again, just like the mass spring system here. So that's where we displace it. So let's go through the same process we did with the springs, looking at how we can get some equations to model it. So let's work out the acceleration to start with. So we need the resultant force divided by the mass. So we're using Newton's second law. So weight force is mg, so we can cancel out the m's, and we actually realise that the mass hanging on a pendulum has no effect on its oscillation, which is fairly interesting. So we get the acceleration is equal to minus g, 9.81, divided by the length of the string, times the displacement. So again, acceleration is directly proportional to the displacement, and we've got some constants which change how that works. So like I did with the mass spring system, I'm going to change acceleration into velocity times dv over dx, and we're going to integrate those. So move the dx to the other side, and we're going to integrate to get rid of those. So we're going to integrate the velocity with respect to velocity and the acceleration with respect to displacement to eliminate those partials. So in terms of where we start the integration from, when we give it initial displacement, its velocity is 0. So our first limit on our velocity integration is 0. We start it from its maximum displacement, or the amplitude. So we start the displacement integration from A. And we want to know the velocity at a given displacement x, so we have v and x respectively. So then we go through, and we first want to substitute in our expression for acceleration in here. So that's what I've done, taking the constants outside. Then I've actually gone through and integrated it with within those limits. I've done some cancelling out. I see I've actually been very sloppy here. There should be a 2 on the bottom line here, should be g over 2l, then those halves cancel out, so that expression is correct, and the minus sign and what's in the brackets has just flipped around. And we get this expression at the bottom, which is very similar to an equation you have in your formula sheet, but not quite, just like we had in the last video, but we can see later on that that becomes the formula sheet equation in a minute. Okay, so that is the first one. So we've got velocity in terms of displacement. Now let's look at getting an equation for velocity and acceleration in terms of time. Okay, so let's have a look at modelling the displacement of the pendulum as a function of time. So we know that when we start it off, we need it to be at its maximum displacement. So that's how we know it's a cosine function. When it's completed one full time period, so gone all the way over here and back, we need it to be at the same displacement as we started with. So that's why we put this 2 pi over t in here. So when t equals 2 pi, t equals the time period, those two t's cancel out and we get back to the same starting position. We need it to start at its maximum displacement, so that's why the whole thing is multiplied by the amplitude there. So that's how we get our displacement equation. And to get velocity, we need to take the derivative with respect to time. So cosine turns into a minus sign, and whatever multiplies by the t comes outside. So we get this expression for velocity. Same again, minus sign becomes minus cosine. Again, multiplying by whatever's inside the brackets. We get this expression over here at the end. So a cosine 2 pi over time period times t is the displacement. So we can cancel all that and just put an x in here. So we get a relationship between acceleration and displacement with some constants in here, either the time period or the frequency. Okay, so let's put all the stuff we've got together and get some of the more of the equations used to model a system. So we've currently got these two equations for the acceleration of our pendulum system. So what we can see is we can equate these two things together. So you can see that frequency is actually going to turn out to be a constant. And that's the case if we don't apply any forces to our system once we've set it oscillating. So we use an external force to initially displace it, but then we apply no other forces to it and we can model it using these equations. So 2 pi f squared is clearly equal to g over L. So we can rearrange that and get an expression for what's called the natural frequency of the pendulum. So how many oscillations you should get per second if you don't apply any forces to it once you've displaced it. So an interesting thing you'll spot is there is no displacement in this equation, just like there wasn't for the mass spring system. So it doesn't matter how far you initially displace it, it will have the same frequency. It also, in the case of a pendulum, doesn't matter what the mass is. You can see that's not in your expression. So again, the natural frequency of a pendulum system, nothing to do with mass at all. So we can flip this whole expression over to get an expression for the natural time period, and that's this expression here, which you will find in the formula sheet in most of your exam papers. But when those of you who get to do engineering at university will see it in this form most often, because we usually model things when we shape them and stuff with a certain frequency. So that's that one. So let's put all of this together and get the last couple of equations that we're going to look at to model SHM. So these ones on the left should be the equations you've seen come from already in this video, and we've also got this one over here on the right for velocity in terms of displacement. So what we can do is we know g over L is equal to 2 pi f squared. We saw that earlier. So what we can do is swap in 2 pi f squared for g over L and take it outside the square root because it's squared, and we get this expression here, which is typically what you have in your formula sheet for velocity at a certain displacement for an object in SHM. Then what we can do is go, well, when is this maximised? Well, when displacement is 0. We can see that because then we're subtracting the smallest possible number here. So we get this expression here for the maximum velocity of our pendulum bob in our system. And we can also get this expression for maximum acceleration by putting this cosine function equal to 1, because that's the maximum a cosine function can be. So here we can see the maximum acceleration is 2 pi f squared a, and if we know maximum acceleration, we know the maximum resultant force acting on an object, so then we can again check that things are safe, for instance, in that case. Okay, so these are all the things that you need to model a pendulum in SHM. The required practicals on this topic then generally will investigate these, and you'll investigate two variables typically. You investigate how the length affects the time period, and you'll investigate how the mass affects the time period, or in this case, doesn't affect the time period. That's what you should find out. And so that's typically where this is going to go next. So that concludes this video, and as I said in my last video, don't worry too much if you don't follow the derivation process. That's for those of you who are a bit more mathematically minded, who are thinking about doing like physics engineering at university. That'll be useful for you. But the keys to take away here are the different equations we have to model an object in SHM, the assumptions we made behind them, i.e. that it's in free oscillation or free vibration, and essentially the conditions of SHM and what factors will affect the time period of a pendulum system. So I hope you found that useful. Do check out my next video I'm making on circular motion, but thank you for taking the time to watch this video.